What if the moon slowly drifted away from Earth forever? The first extra distance is smaller than a grain of salt. At 2:43 in the morning, Dr. Leora Vale is sitting beneath a mountain in southern Spain, watching a green laser strike the moon and return as a handful of exhausted photons. The observatory dome above her is open to a cold, clear sky. On a monitor, the round-trip travel time appears as a line of digits. Most of those digits mean nothing by themselves. The atmosphere has delayed the pulse. The observatory floor has expanded. Earth's crust has shifted under the building by fractions of a millimeter. The moon itself is never at one fixed distance. Leora has spent 19 years learning how to remove everything that is not the moon. The laser pulse left Earth and crossed almost 400,000 kilometers of space. It struck a corner cube reflector placed near the lunar south pole 12 years earlier, then returned to a telescope that received only a few photons. The timing system converts that fragile return into distance. The result is compared with the orbit predicted by gravitational models, planetary ephemerides, ocean tides, atmospheric pressure, snow load, groundwater, polar motion, and the slight flexing of Earth under the pull of the Sun and Moon. The Moon should be 384,721,604,112 millimeters from the reference point at this instant. It is 384,721,604,119. 7 millimeters too far. Leora does not announce a discovery. 7 millimeters is what an observatory calls an invitation to distrust itself. She checks the clock. She checks the atmospheric profile. She checks whether the reflector coordinates were updated after a moonquake. She asks the night technician to inspect the calibration path without telling him the direction of the error. He finds nothing. She waits for the next pulse train. The second result is 8 millimeters too far. The third is 7. At another observatory in Arizona, a different team is measuring an older Apollo reflector. Their result arrives through the Secure Scientific Network at 3:16. 6 millimeters too far. A station in Western Australia reports 9. The numbers are not identical because the geometry is different, but the residual points outward in every case. The moon is already moving away from Earth in the ordinary universe. Laser ranging has measured an average recession of about 3.8 centimeters each year. Ocean tides are part of the reason. Earth rotates once in roughly 24 hours, while the moon takes much longer to orbit. The tidal bulges raised on Earth are carried slightly ahead of the line between the worlds. Their gravity pulls the moon forward, adding orbital angular momentum and lifting it slowly into a larger orbit, while tidal friction takes a little rotation from Earth. That process is ancient, uneven, and deeply dependent on the shapes of oceans and continents. The present rate cannot simply be carried backward or forward for billions of years. Today's ocean basins happen to dissipate tidal energy efficiently. Past arrangements did not always do so, and future arrangements will not either. In the ordinary future, the recession would change, the sun would evolve, and the Earth-Moon system would never have unlimited time to settle into its distant theoretical end state. The 7 millimeters on Leora's screen are not the ordinary recession. They are 7 millimeters beyond it. By sunrise, 12 stations and 3 spacecraft tracking networks agree. The residual crossed the network's detection threshold 11 days earlier. Retrospective analysis places the onset roughly 2 months before the night Leora first sees it, and the extra distance has grown smoothly since then. The moon is receiving a minute outward acceleration that no accepted model contains. It is not losing mass. Earth's gravity has not weakened. The gravitational constant appears unchanged in laboratories and planetary orbits. The moon's path has not been struck by an asteroid. No engine burns on the far side. The unexplained force acts almost exactly along the direction needed to increase the size of the lunar orbit. Leora drives home after 31 hours awake. Her daughter, Selene, is waiting at the kitchen table with 2 cups of coffee and a school assignment about eclipses. Selene is 16 and has inherited her mother's habit of asking a question only after she has already found half the answer. "Is it true?" she asks. "What have you heard?" "That the moon jumped." "It did not jump." "That means yes. It moved 7 millimeters farther than expected." Selene looks toward the brightening window. The moon is below the horizon. "Can anyone see that?" "No." "Can anyone feel it?" "No." "Then why do you look frightened?" Leora sits across from her. On the table, Selene's assignment shows a diagram of the sun, moon, and Earth aligned in a row. The moon is drawn much too large and much too close, as it always is in diagrams meant to fit on paper. Because the 7 millimeters are not the important part, Leora says. The important part is that we do not know who paid for them. Orbital energy and angular momentum do not appear from nowhere. If ordinary tides move the moon outward, Earth's rotation provides the transfer. If a rocket moves a spacecraft, propellant and exhaust carry momentum. The new acceleration has no visible partner. Something outside the familiar Earth-Moon exchange is applying a torque. Within a week, the effect receives a temporary name, the outward term. Within a month, the temporary name has become permanent because every alternative sounds too dramatic. Newspapers prefer the leaving. Scientists continue saying outward term in public and much worse things in private. The first models are reassuring. The inferred extra recession rate is close to 4 centimeters per year. If that rate remains fixed, the moon will gain only a few tens of meters over many centuries. Tides will change imperceptibly. Eclipses will remain. Lunar travel will require slightly different navigation. Humanity has survived larger orbital uncertainties in its own planning mistakes. Then the outward term strengthens. Not quickly, not enough for anyone to see the moon move. Every 28 years, the additional recession rate doubles. At first, the pattern is only a fit through a short and noisy record. After 11 years, multiple instruments detect curvature. After 22, the curvature is undeniable. The force is exponential on human timescales and gentle on daily ones. It does not act on artificial satellites. It does not push Earth away from the sun. It couples to the moon's bound orbit around Earth, adding energy and angular momentum from an unknown external reservoir. The source remains unexplained. Dark matter detectors see nothing. Solar activity does not correlate. The effect persists through eclipses, lunar phases, magnetic storms, and changes in Earth's orientation. It is slightly stronger near apogee than perigee, as though it recognizes the shape of the orbit. The best equations describe what it does and remain silent about why. Leora dislikes equations that behave like instructions without an author. Selene likes them immediately. By 26, she is an orbital engineer working at Shackleton City near the lunar South Pole. The settlement began as a cluster of research modules around permanently shadowed ice deposits. It has become a network of buried pressure halls, solar towers, mines, greenhouses, observatories, and launch rails. From its sunlit ridges, Earth hangs above the horizon as a blue-white world almost 4 times wider in the sky than the moon appears from Earth. The outward term has added less than a meter to the mean Earth-Moon distance since Leora's first night. No lunar resident needs extra fuel because of it. No tide table has been rewritten for it. Yet every permanent structure in Shackleton carries 2 design dates: the year it becomes operational and the latest year it can remain useful if the doubling law continues. A rail launcher built for cargo to Earth orbit may serve for 90 years. A communication array may serve for 140. A buried habitat can last centuries if people still choose to inhabit it. A memorial carved into rock can last longer than the relationship it commemorates. Selene calls Leora each Sunday. The delay remains just over a second each way. They still interrupt one another. You are designing an evacuation schedule for a city that is not in danger, Leora says during one call. I am designing options. You have been there 4 years, which is long enough to notice that Earth calls every planned evacuation if it ends with people somewhere else. Leora hears the sentence and does not answer quickly. Shackleton is no longer a remote station staffed by rotating crews. Children have been born there. Families have buried ashes in sealed lava tubes. Some residents have never stood under rain. They do not consider the moon a vehicle carrying them away from home. They consider it home moving through a changing sky. The first century of the leaving is an age of arguments about preparation for changes nobody alive will see. Coastal governments commission new tidal maps, then cancel them when the projected difference remains smaller than storm variability. Insurance firms add lunar recession clauses to contracts lasting more than 50 years. Religious authorities debate whether calendars tied to lunar months should follow the changing astronomical cycle or preserve inherited dates. Engineers propose moving every major lunar industry towards self-sufficiency. Economists ask who will pay for infrastructure needed by grandchildren who may choose not to use it. People mock the plans because mockery is cheaper than copper, water, or launch mass. The moon still looks the same. Its measured orbit does not. Selen and Leora help establish the Long-Range Archive, a chain of records stored on Earth, the moon, and stations between them. Every 28 days, the archive saves observations that no future theory can reinterpret completely. It records the measured distance, orbital speed, length of Earth's day, tides at thousands of coasts, apparent sizes of moon and sun, and a photograph made with known geometry. The archive also saves voices. Leora records the first entry. The moon has moved farther than expected, she says. Nothing visible has changed. That sentence is how this story begins. Selen records the second from Shackleton. Earth is still large in our sky. Nothing visible has changed here either. That does not mean the two sentences describe the same future. Leora lives to 93. By the year she dies, the anomalous recession rate has grown from a few centimeters per year to roughly 1/10 of a meter per year, several times the natural tidal recession that first taught humans how to measure the separation. The total extra distance is still less than the height of a room. The moon remains where every human eye expects it. Her final visit to the observatory occurs in a wheelchair. The night staff lowers the instrument controls so she can reach them. Selen has returned from the moon for the first time in 8 years. She stands behind her mother while the laser fires. The returned photons arrive. The measured distance appears. Leora's Tomas spends 40 years telling councils that weaker average forcing does not mean every coastal risk becomes smaller. At the Bay of Fundy, the great tidal range declines slowly, then stabilizes for a generation as sea level change and basin geometry compensate. In a shallow engineered sea in northern Europe, a resonance shifts and local tides temporarily grow even while the moon's force weakens. A tropical delta loses the regular flushing that once carried sediment and nutrients through mangrove channels. Engineers open gates to imitate part of the missing rhythm. Fish use the gates before governments finish arguing over who owns the Ira answers. The object moving away is the moon. The people choosing abandonment are still being identified. The sentence travels through both worlds. Selen, now long dead, has become one of the founders children memorize in school. Leora's first 7mm are displayed in museums. The Long-Range Archive continues adding measurements. Each generation records that the moon still appears almost unchanged to the naked eye. Then the first visible change arrives not in the moon itself, but in an eclipse. The eclipse occurs over the South Pacific in the year 2446, 348 years after Leora's first measurement. It is not the last total solar eclipse. It is the first one whose path fails to match an old prediction by more than the uncertainty of weather and Earth's rotation. Astronomers have known for centuries that eclipse calculations must include the moon's changing orbit. The outward term is already built into every modern ephemeris. Nothing surprises the professionals. The surprise belongs to the public, because a printed map from a childhood textbook shows totality crossing an island that now receives only a bright crescent of Sunday. The lunar shadow passes 80 kilometers north. People who waited on the island see the sky dim, but not close. Birds quiet. The sea changes color. A narrow ring of sunlight remains. On ships to the north, totality lasts 43 seconds. The misplaced expectation becomes more famous than the eclipse. Old maps are collected. Families compare inherited calendars with current predictions. The leaving, previously known through graphs and policy documents, enters memory as something that can move darkness away from people who were promised it. Ira attends the eclipse from a vessel operated jointly by Earth and lunar universities. She is 81 and has spent 4 decades negotiating the shrinking usefulness of the word temporary. Beside her stands her grandson, Aaron Vale, an 11-year-old born in Shackleton. Aaron has never seen a natural sky without glass or a suit. He watches the sun vanish through a filtered viewport while the ship rolls on a slow ocean. During totality, the solar corona spreads beyond the black disk of the moon. Aaron removes his eclipse visor only when the automated frame and 3 human observers agree. He looks for 43 seconds. Then sunlight returns around the lunar limb. Did it used to last longer? He asks. Sometimes. Will I see another? Yes. Will my children? Ira looks toward the navigation display. The question has a mathematical answer with error bars. She gives him the human one. If they decide it matters enough to travel. By Aaron's adulthood, travel matters more than almost anything. The moon's anomalous recession rate has reached hundreds of meters per year. The accumulated extra distance approaches 10 kilometers, then 30. The change remains small compared with the whole orbit, but the future no longer arrives evenly. Each doubling adds as much recession rate as every previous doubling combined. Infrastructure designed during Aaron's childhood becomes obsolete before his children inherit it. The old gravitational balance regions between Earth and Moon move outward. Transit stations migrate. Cislunar navigation loses the comforting fiction of permanent lanes. A cargo depot that once needed modest station keeping begins spending more propellant every year because its orbit was designed around a geometry that will not return. Insurance markets stop offering lifetime coverage to fixed orbital assets. Everything built between the worlds must be mobile, disposable, or honest about its closing date. Aaron becomes a trajectory planner. He does not design the moon's path. The outward term has already done that. He designs paths for everything that must decide whether to follow. The Lunar Commonwealth now supports nearly 20 million people. Its cities are not self-sufficient in the simple sense used by early planners. No large civilization is. Lunar agriculture can feed the population in calories, but seed diversity, microbial cultures, medicines, precision catalysts, and living genetic libraries still move between worlds. Earth depends on lunar vacuum industry, isotope production, observatories, and mass launched cheaply from low gravity. Each side can survive without the other. Neither can remain unchanged. The separation debate begins with transportation and becomes a referendum on identity. Earth's coalition proposes the Return Compact. Over 2 centuries, anyone wishing to leave the moon will receive transport, medical adaptation, and residence in rotating habitats where gravity can be increased gradually before arrival on Earth. Lunar industrial equipment judged essential to both worlds will be duplicated or relocated. Cultural archives will be copied. No person will be compelled to stay on a body approaching uncertain orbital conditions. The Lunar Assembly proposes the Companion Compact. Earth will help build a self-sustaining moving civilization on and around the moon. People who remain will retain Earth citizenship if they want it, even after ordinary travel becomes costly. Communications, scientific exchange, emergency aid, and family law will continue across increasing distance. The moon will not be treated as a failing station to be evacuated, but as a world whose orbit is changing. Both plans require more resources than either side has promised. The Return Compact is accused of stripping lunar society of engineers, children, and reproductive diversity while leaving mines behind. The Companion Compact is accused of romanticizing a journey nobody can reverse. Families divide. Some parents send children earthward and remain. Some children refuse. A person can love the moon and still leave it. A person can fear the future and still stay. Aaron's wife, Dahlia, was born in an orbital habitat and can tolerate both lunar and near-Earth gravity. Their two children make opposite choices. Sayo returns toward Earth to study ocean dynamics. Kest remains at Shackleton and enters the navigation service. At the departure terminal, Dahlia gives Sayo a small sealed box containing the garden soil selenite brought from Earth generations earlier. The Lunar Archive has preserved it for more than 2 centuries. "You are sending Earth to Earth," Sayo says. "I am sending a witness," Dahlia replies. "What does soil witness?" "That nobody travels empty." Kest watches the transport rise from the lunar horizon. Because the moon is tidally locked, Earth still hangs in nearly the same place above Shackleton, rocking slightly through libration. It has become imperceptibly smaller. Kest knows the measured change. Her eyes do not. She will live long enough to see that become untrue. In the 5th century of the leaving, the moon's extra distance grows through hundreds of kilometers. Its orbital period lengthens measurably. The lunar month changes enough that school children no longer use the old number except in history lessons. The light time adds milliseconds, then hundredths of a second. Conversations still feel immediate. Automated systems notice every delay. Tides on Earth weaken in their lunar component. At twice the present distance, the moon's tide-raising influence would be about 1/8 as strong, but the system has not reached twice the distance yet. The early decline is modest. Solar tides become a larger fraction of the whole. Spring tides and neap tides change because the competition between sun and moon changes. Coastlines continue to have tides, but their inherited rhythm becomes less lunar and more local. Sayo works in the estuary of a city whose river once relied on strong spring tides to move sediment. Engineers have already deepened channels, removed walls, restored wetlands, and built gates that pulse water according to ecological schedules. The gates do not imitate every natural tide. They cannot reproduce the gravitational movement of an entire ocean. They restore enough variation for mudflats, fish nurseries, salt marshes, and navigation. People argue that an artificial tide is no tide at all. The birds do not care what the argument is called. Other coasts change differently. Some harbors require less protection from routine high water. Some tidal power plants close as output falls. Others convert to current, wave, solar, or storage facilities. Intertidal species migrate downshore where geometry permits. On armored urban coasts, there is nowhere to move. Conservation programs transport organisms and recreate habitats. Success is uneven. The leaving does not remove human responsibility by moving slowly. At night, lunar illumination declines with the square of distance. Again, the first changes are subtle. A full moon remains bright enough to cast shadows. Nocturnal animals adjust behavior. Predators hunt slightly closer to dusk. Prey spend longer in open ground. Corals that once used a combination of lunar light, temperature, and tidal timing continue spawning, but the signal's separate. Evolution finds new cues where populations survive long enough. Human beings build brighter cities and then create dark reserves to remember what unlit moonlight looked like. Kest becomes director of the Far Orbit Service. Her maps show a future in which the moon crosses the distance beyond which total eclipses become impossible. The threshold is not one perfectly sharp radius. The moon's orbit is elliptical. Earth's orbit around the sun is also elliptical. The apparent sizes of both bodies vary. Totality disappears first from some geometries and survives in rare combinations when the moon is near its closest and the sun near its apparent smallest. The last total eclipse cannot be predicted to one date centuries in advance because the outward term contains small fluctuations. It can be narrowed to a cluster. The Eclipse Commission is formed 90 years before the expected end. The name sounds ceremonial. Its work is technical and severe. It must preserve observation sites, calculate shifting paths, control traffic, prevent unsafe mass gatherings, protect ecosystems, and decide whether the final total eclipse belongs to science, heritage, tourism, religion, or nobody. Kest opposes the word final. It is final only from Earth, she says. People elsewhere may still see the moon cover the sun from another geometry. The Commission changes the official phrase to the last terrestrial totality. The public keeps saying final. By then, the extra Earth-Moon distance is thousands of kilometers and rising by hundreds of kilometers each year. The moon is visibly smaller to careful observers. Photographs taken with the same lens across generations show a change no one can dismiss. Lunar residents see Earth shrink too, though much less dramatically because the same physical separation affects the apparent size from both sides. Transport costs rise faster than distance alone suggests. Transfer times lengthen. Orbital speeds change. The gravitational architecture that once allowed elegant low-energy pathways becomes unstable under the accelerating orbit. Vehicles must carry wider margins. Rescue windows narrow. Passenger service becomes less frequent and more like migration. The return compact enters its final phase. Most people who intended to leave have left. The lunar population falls from 20 million to 12, then stabilizes. Those who remain are not stranded miners or romantic volunteers. They are a civilization with closed agriculture, deep reserves, independent industry, medical ecosystems, and habitats built to survive long interruptions. They know that independence is never complete. Earth also depends on systems beyond any one nation or continent. Survival means having enough ways to fail without failing all at once. Kest's daughter, Malin Vale, is born during the last century of ordinary travel. She becomes a historian of orbital law, a field that once would have sounded like a contradiction. Her work concerns contracts whose parties occupy worlds moving toward different futures. Can an Earth court claim jurisdiction over a lunar archive after the moon leaves Earth orbit? Does a marriage remain governed by the law of the place where it began? Who owns a mining lease whose coordinates were defined relative to a planet no longer orbited? Can lunar citizens vote in Earth elections when messages take minutes and journeys take years? Does planetary citizenship require The partial phase is already deep. The moon appears as a dark curve advancing across the sun. Instruments measure its angular diameter. Weather balloons report the atmosphere. Navigation teams refine the shadow path minute by minute. The central platform adjusts position by 200 meters. At second contact, sunlight narrows into broken beads along lunar valleys. For less than 4 seconds, the final bead disappears. The photosphere is gone. The corona opens around a moon only barely large enough to contain the sun. Totality lasts 1 second and 8/10 at the center line. Many human beings blink and miss it. Oren does not. She sees darkness become complete and immediately begin to break. A point of sunlight returns at the lunar edge. Totality ends for Earth, not with a long night, but with a single impossible-looking spark. Malin is crying. Orin takes her hand. On the moon, Orin says, Earth still eclipses the sun. Malin laughs through tears. I know. I thought it might help. It does. The last terrestrial totality becomes the most recorded event in history and one of the least reproducible. Every recording can show the geometry. None can reproduce the knowledge that a natural event repeated across hundreds of millions of years has crossed a boundary. Afterward, annular eclipses continue. The moon still passes before the sun. A ring of light remains. Children born later do not experience the ring as a lesser version. It is simply what an eclipse is. The end of totality does not change tides, climate, or orbits. It changes the public understanding of time. The leaving is no longer a prediction. It has taken something the sky will not give back. During the same decade, the orbital models cross a more dangerous threshold. The moon will not remain securely bound to Earth if the outward term continues. Far from Earth, the sun's perturbations become increasingly important. The region in which Earth can dominate a satellite is finite. The exact escape path depends on lunar phase, orbital inclination, solar geometry, and the continuing external torque. A simple statement that the moon will reach one distance and fall free is not accurate. The transition will be chaotic. A poorly timed crossing can place the moon on a heliocentric path that returns for repeated close approaches to Earth. A close approach does not mean collision. It can still disturb satellites, habitats, debris, and the carefully managed orbits of both civilizations. It can change the moon's path again and prolong uncertainty for centuries. The outward term appears to weaken as Earth's control weakens, suggesting that it couples specifically to a bound Earth-Moon relationship. That is good news. It also means the final trajectory will be decided during a narrow interval when ordinary solar gravity, Earth gravity, and the fading anomaly are comparable. Human beings cannot stop the moon. They may be able to choose how it leaves. The proposal is called clear departure because every other name sounds like ownership. Its purpose is not to hold the moon near Earth. No plausible industry can provide the angular momentum needed to cancel an external torque that doubles on schedule. Its purpose is narrower. Over more than a century, lunar mass drivers will eject carefully chosen streams of processed regolith and slag at high velocity. The reaction will alter the moon's motion by only a fraction of a millimeter per second. Near the unstable boundary between an Earth-bound orbit and a solar orbit, that tiny difference can shift the timing of future encounters by thousands of kilometers. The engineers compare it to touching the edge of a falling leaf. Critics compare it to firing pieces of a world into space because equations have become frightening. Both descriptions are true enough to attract followers. The total expelled mass will be enormous by human standards and negligible compared with the moon. Mines already move comparable material over decades, but not with one purpose and not at such speed. The energy must be collected over generations in orbital solar arrays, stored in rotating masses and superconducting systems, and released through launchers distributed across the lunar far side. No single state or city can control the impulse. The launch sequence requires independent agreement among Earth observatories, lunar navigation centers, solar monitoring stations, and crews on the surface. Clear departure will not guarantee safety. It will replace a broad family of poorly constrained returns with a narrower family of heliocentric paths designed to carry the moon slightly outside Earth's orbit around the sun. The moon will become a separate small world moving on a year somewhat longer than Earth's. It will drift behind. Later planetary perturbations may change that path, but immediate repeated close approaches become far less likely. The Lunar Assembly supports the plan by a narrow majority. Earth's coalition divides. Coastal states fear any intervention that might alter the final tidal decline. Space habitats fear debris. Religious communities object to deliberate modification of the moon. Other groups argue that refusing a small controlled correction when an uncontrolled passage threatens two worlds would be a greater act of arrogance. Malin Vale testifies before the Joint Council. "You are not voting on whether the moon remains natural," she says. "The premise has already removed that choice. You are voting on whether knowledge creates responsibility when control is incomplete." A delegate asks whether she can promise Earth will be safe. "No." "Can you promise the lunar cities will survive the operation?" "No." "Then what can you promise?" "That every uncertainty we know will remain visible in the decision record." The delegate calls this insufficient. Malin agrees. Clear departure begins anyway. The first mass driver is built near the lunar far side equator, where launches can be aimed without crossing the space between Moon and Earth. It is a trench longer than a city, lined with electromagnetic stages. Processed rock enters as dense packages. The system accelerates each package until it becomes a stream of glowing grains moving fast enough to escape the Moon and join independent solar orbits. No explosive plume rises. In vacuum, the launch is a vibration through the ground and a temporary line of light above the horizon. The reaction on the Moon is immeasurably small in one launch. The archive measures it anyway. More drivers follow. They do not all fire in the same direction. Some correct inclination. Some reduce eccentricity. Some are reserved for the final phase adjustment. Every impulse is paired with observations from distant stations. If the orbit responds differently from the model, the sequence pauses. For 70 years, the system works so gradually that most people forget it is operating. Then the Moon stops, showing Earth the same face. The first sign is not a dramatic rotation. It is a mismatch in libration. The Moon has always appeared to nod and turn slightly because its orbit is elliptical and tilted, allowing Earth to see about 59% of the lunar surface over time. Its spin period matched its orbital period closely enough to maintain synchronous rotation. As the outward term lengthens the orbit more quickly and lunar tidal torque weakens with distance, the Moon's spin cannot slow at the required rate. The lock begins to slip. At first, the familiar near side drifts by only a fraction of a degree over years. Lunar cartographers notice before the public. Then old craters approach the limb and remain there. New terrain appears from the far side, not through a spacecraft image, but from Earth's sky. People gather with telescopes to see mountains no unaided human eye has ever seen from the ground. The event has no official date. Tidal locking does not switch off like a machine. There is only a period when the old face no longer returns to its expected orientation. The man in the Moon deforms. The familiar dark Maria slides sideways. The bright far side highlands rotate into view. On the Moon, Earth begins to move across the sky. For settlements near the old near side, Earth had hung in nearly one place for centuries. Communication dishes could be built into fixed structures. Artists designed windows around the blue world. Children used it as a direction. As the spin and orbit separate, Earth starts a slow journey along the lunar sky. It rises where it never rose before and sets where it never set. Shackleton, near the pole, sees the change as a broad wandering around the horizon. Equatorial cities experience full Earth rises and Earth sets. The old far side sees Earth directly for the first time. People who grew up beneath an earthless sky camp on ridges to watch a blue edge appear. The sight is delayed by dust and geography. The first visible sliver rises above mountains in the basin of Korolev. It is smaller than Earth appeared to the early lunar settlers, but still bright enough to color the black sky around it through the eye's own response. The crowd is silent until someone begins reading Selenvale's first lunar archive message. Earth is still large in our sky. Nothing visible has changed here either. The sentence is 6 centuries old. Everything visible has changed. The breaking lock alters lunar life more directly than the increasing distance. The solar day on the moon no longer matches the orbital month in the old way. Sunlight cycles shift. Power systems built around 2 weeks of day and 2 weeks of night must adapt. Polar illumination patterns change less, but equatorial agriculture, thermal systems, and surface travel schedules are redesigned. The moon's rotation remains slow by Earth standards, yet it is no longer a simple calendar. Some lunar citizens experience the moving Earth as liberation. The permanent near side and far side had shaped politics, communication, and culture. Near side cities enjoyed direct links. Far side observatories enjoyed radio silence and isolation. Now every longitude alternates between connection and concealment. Others experience it as loss. A person can miss a world that still rises every few months. Orenvale spends her adult life preparing for the breaking lock. She becomes a navigator because no map remains emotionally neutral. Her mother teaches her the old sky. Her instructors teach the new one. She can calculate the moon's changing rotation from radar and star trackers, but she also learns to ask residents which Earthrise they consider the first. By the time Oren is 75, the mean Earth-Moon distance has increased by more than 100,000 kilometers beyond the ordinary path. The moon's apparent diameter from Earth has declined substantially. Its full phase remains one of the brightest objects in the sky, but the difference is obvious. Moonlight casts paler shadows. Photographers use longer exposures. Poets stop comparing round faces to the full moon unless they intend nostalgia. The orbital period has grown. The interval between similar lunar phases stretches. Solar tides now dominate many components that lunar tides once controlled. The moon still raises oceans, but its direct tide-raising influence has fallen sharply. There is no tideless Earth. The sun continues pulling. Winds, pressure, coastlines, and basin resonances continue moving water. The daily pattern remains complicated and place-specific. The intertidal world becomes narrower in many regions. Salt marshes migrate where land is available. On developed coasts, managed flooding creates artificial zones. Some species that depended on strong lunar cycles disappear. Others adapt to solar rhythms or temperature. Ecologists resist the temptation to describe the result as a simpler sea. Removing one strong influence allows weaker and local influences to become more important. Earth's rotation continues slowing under solar and residual lunar tides, but more weakly than it would with a nearby moon. The length of day has not become a major human problem. Civil time is defined by atomic systems. The natural day remains close enough to inherited patterns that bodies and ecosystems adapt gradually. The deeper concern is Earth's axial stability. The moon's gravity has helped keep Earth's obliquity within a relatively narrow range by changing the spin axis precession in a way that avoids broad chaotic resonances with planetary perturbations. A distant moon provides less stabilizing torque. When the moon leaves, Earth does not immediately tip over. The axis has inertia. Climate does not change because one orbital crossing occurs. Over hundreds of thousands and millions of years, however, the range of possible obliquity variation may grow. Models disagree about exact amplitudes because the future solar system, Earth's rotation, continents, oceans, and remaining satellites all matter. Some trajectories remain relatively moderate. Others allow much larger changes than the familiar few degrees. Seasons could strengthen, weaken, or reorganize on timescales long enough for evolution and civilization to respond, but not long enough to ignore forever. Clear departure includes no machine capable of stabilizing Earth's axis. A separate project begins, the precession watch, designed not to fix climate but to measure the changing resonances for as long as humans or their descendants can maintain instruments. Artificial satellites can contribute torque only in fantastically small amounts unless built on a planetary scale. Climate engineering can respond to sunlight patterns more easily than moving an axis. The honest plan is observation, adaptability, and preservation of options. This disappoints people who expect advanced civilizations to solve every orbital problem with machinery. Oren says, being able to move a mountain does not mean you can move a planet responsibly. Clear departure enters its final 50 years. The Moon is approaching the outer region of stable Earth-centered motion. Its orbit is no longer well described by an ellipse with Earth at one focus. Solar gravity pulls strongly across the system. Each lunar circuit becomes a three-body path, stretched and reshaped by the Sun. The outward term weakens as predicted, but not smoothly. It arrives in pulses near orbital phases where the Moon moves away from Earth along the direction of solar motion. The final escape window narrows to 11 days. During those 11 days, the Moon will pass through the geometry in which the remaining driver impulse can shift it toward the selected exterior heliocentric path. Fire too early, and the correction is partly canceled by Earth's gravity. Fire too late, and the Moon enters a family of trajectories with possible returns. Fire too strongly, and the new solar orbit separates faster than lunar supply systems are ready to tolerate. Fire too weakly, and the result may remain ambiguous for decades. The operation is named 11 Days by people who dislike official names. Oren is appointed Chief Independent Navigator. The title means she does not command the drivers. She certifies whether the observed state remains within the corridor approved by both worlds. 3 other navigators hold equal authority. Any 2 can pause the sequence. Restart requires new measurements from Earth, Moon, and solar orbit. Her appointment is attacked immediately. The Vale family has been connected to the leaving since the first measurement. Some call that experience. Others call it inherited power. Oren agrees to publish every model, uncertainty range, dissenting calculation, and personal conflict. She steps aside from decisions involving the family archive. She refuses requests to perform the role as a symbol. I am not here because my ancestors saw 7 millimeters, she tells the Joint Assembly. I am here because I have spent more than 80 years navigating the orbit that followed. The cities prepare. Lunar surface structures secure equipment against continuous driver vibration. Farside launch zones evacuate. Orbital habitats move away from projected ejecta corridors. Earth satellites enter conservative configurations. Coastal agencies publish tide forecasts under multiple possible lunar paths. Hospitals on both worlds stock supplies. Communications networks rehearse delays and interruptions. People also prepare in ways no plan requires. On Earth, families go outside to look at the Moon while it still belongs to the category of satellite. On the Moon, families watch Earth cross the sky and debate whether belonging can be changed by a line in an orbital elements table. Museums open through the night. Temples, observatories, schools, bars, and transit halls carry the same countdown. The Moon does not know the countdown exists. On the first day, the drivers fire for 17 minutes. The impulse is smaller than planned because a star tracking array reports a discrepancy. Oren calls a pause. Engineers find thermal distortion in one far-side reference frame. The orbit itself matches prediction. Firing resumes 6 hours later. On the second day, a solar storm disrupts communication with 2 Earth stations. The operation continues because no single station is required, but the uncertainty widens. One navigator votes to pause. The others agree before debate begins. On the third day, the Moon passes through a region where Earth's gravitational influence and the Sun's differential pull nearly balance along the departure direction. The old language of perigee and apogee becomes less useful. The path bends around no simple center. On the fourth day, one mass driver loses a containment ring. No one is injured. The driver shuts down, reducing symmetry. Other sites compensate within previously approved limits. On the 5th day, a false message claims that the lunar assembly has withdrawn consent. The signature is valid under ordinary systems, but political authority for 11 days requires live confirmation from distributed assemblies. The firing pauses for 22 minutes while representatives appear in separate chambers and verify the vote through independent channels. The message is traced to a group that believes any deliberate impulse makes the moon a weapon. Their fear is not dismissed. Their method is. On the 6th day, Earth's oceans record a high tide lower than old historical averages and still high enough to flood a storm-battered coast. The images become a warning against saying tides are ending. Water answers many forces at once. On the 7th day, Orin sleeps for 3 hours while another navigator watches the corridor. She dreams of a moon falling toward Earth, though every measurement shows it moving away. On the 8th day, the final stored momentum systems spin to full release speed. They have accumulated energy for decades. Nothing on the surface looks dramatic. Beneath the ground, rings the size of cities turn in evacuated chambers. Their eventual release will not hurl the moon forward like a spacecraft. It will help power a precisely timed sequence of ejected mass. On the 9th day, the projected return probability falls sharply in most model families. A minority model still shows a close approach in 900 years. Its assumptions require the outward term to reverse sign after escape. No evidence supports that reversal. No evidence can rule it out absolutely. The descent remains in the record. On the 10th day, Earth and Moon exchange no ceremonial speeches. Bandwidth is reserved for measurements and safety. Public channels carry old recordings from the long-range archive instead. Leora says, "The moon has moved farther than expected. Nothing visible has changed." Selen says, "That does not mean the two sentences describe the same future." Ira says, "The people choosing abandonment are still being identified." The voices arrive on both worlds with several seconds of delay. On the 11th day, the remaining drivers fire. The launch streams begin before dawn at Shackleton, though dawn has lost the meaning it held when the moon kept one face toward Earth. Across the far side, thousands of accelerator stages pulse in sequence. Packets of refined regolith enter as solid masses and leave as expanding lines of grains. Each grain carries momentum away. Each launcher receives a reaction too small for a human body to feel and large enough, when added to every other reaction, to matter at the boundary of worlds. Orin watches the measured state rather than the firing schedule. Position, velocity, solar angle, lunar rotation, Earth's motion, the fading outward term. Each arrives from multiple instruments. No one number decides. The approved corridor is a volume in a space of possible futures, and the moon is moving through it. At 0418 coordinated time, the first major momentum release begins. The underground rings transfer stored energy into the driver network. Surface crews report vibration like distant machinery. In Korolev Basin, loose dust lifts from equipment legs and settles again. In Shackleton, water in a transparent maintenance tube trembles. Earth sees nothing without instruments. The moon remains a pale disk in daylight. At 0502, one navigation solution places the future path near the inner edge of the corridor. The difference from the central model is less than the width of a city after 2 decades of projection. Orin asks for an independent reduction. The second solution agrees. A third does not. The disagreement comes from a solar pressure correction applied to one tracking platform, not to the moon. The platform model is fixed. Firing continues. At 0647, the measured change in lunar velocity reaches 42 micrometers per second. At 0911, it reaches 90. The target is not one fixed number. It depends on the outward term during the window. Every hour, The required correction is recomputed. The force that began the leaving is weakening as Earth's grip weakens. For the first time in centuries, its future contribution is smaller than its uncertainty. At 12:30, a lunar city requests a pause because vibrations have triggered a pressure warning in an old lava tube district. The warning proves false, caused by a sensor mount. Orin votes to pause anyway. The corridor remains available for 4 more hours. People matter more than efficiency. Firing stops. The silence is strange. For 11 days, the moon has been a machine in public imagination. During the pause, it becomes rock again. Crews inspect the district. No leak is found. Residents vote locally to permit resumption. The joint authority accepts the vote. At 13:26, the drivers restart. The final required increment is 31 micrometers per second. One launcher array has already exhausted its prepared mass. Another is operating below temperature limits. The remaining impulse can still be achieved, but the distribution shifts. Orin checks whether the asymmetric firing will excite lunar rotation or alter the selected plane. The effect is within tolerance. She confirms. At 15:03, the last mainstream leaves the far side. No bell rings. The navigation displays continue updating. A planned reserve remains available for 20 minutes if the state falls outside the corridor. It does not. At 15:24, the reserve window closes. The moon has received a total deliberate velocity change of less than 0.2 of a millimeter per second across the full century of clear departure, with only a small final fraction delivered during 11 days. A person walking slowly moves millions of times faster. Yet the correction has shifted the phase of the future heliocentric path enough to reduce the chance of repeated near-Earth returns in every model that does not invent a new reversal of the anomaly. Orin does not announce success. She says, the measured state is inside the departure corridor. The sentence disappoints broadcasters and relieves engineers. The moon is still gravitationally influenced by Earth. It does not cross an invisible wall at that instant. For months, the path remains ambiguous to ordinary language. It loops through the outer Earth-Moon region while the Sun pulls more strongly on its future. Some orbital definitions still classify it as a satellite. Others do not. Legal systems request a date. Dynamics refuses to provide one. The Long-Range Archive chooses not to declare departure until the Moon completes a full solar orbit without returning to an Earth-centered loop. That takes more than a year. During the waiting period, tides continue changing. Lunar residents continue working. Earth and Moon continue trading through ships already in transit. Families continue arguing. Nothing feels like the day after an ending because the ending is an orbit, not a door. 6 months after 11 days, the Moon passes beyond the distance at which early laser ranging would have been practical from Earth's surface. Modern arrays still track it through optical, radar, and transponder measurements. Leora's green pulse has become a network of interferometers spread across millions of kilometers. 9 months after, the Moon's path around the Sun is visibly distinct from Earth's. It remains close enough in heliocentric space that the two worlds share nearly the same season, but not the same year. Earth moves ahead. The Moon begins to trail. 14 months after, the archive declares that Earth no longer has a natural satellite of lunar mass. The declaration is not unanimous. Some scientists argue that temporary capture definitions should be applied over longer intervals. Some lunar citizens reject Earth's authority to define what the Moon is. Some people continue calling it the Moon because names are not orbital classifications. The public statement uses 3 sentences. The Moon has left its long-term Earth-centered orbit. It now follows a heliocentric orbit close to, but distinct from, Earth's. It remains inhabited. Orin reads the statement from a navigation hall in Shackleton. Earth is below the horizon. It will rise again because the Moon's rotation continues. not because the moon circles Earth. Afterward, she goes outside in a suit with no official escort. The sky is black. The sun is low. The lunar ground carries tracks from machines built before she was born. Above the horizon, stars do not show the departure. Constellations remain almost unchanged. Oren thinks of the phrase drifted away forever. Forever is not a measurable interval. The moon has entered a solar orbit that future planets can perturb. It may one day encounter Earth again. It may be captured by nothing. It may survive the changing sun or be altered beyond recognition. No honest scientist can promise an infinite separation. What has ended is the old gravitational partnership. For more than 4 billion years, Earth and Moon shaped one another. The Moon raised tides. Earth slowed the Moon's spin until one face remained turned inward. Tidal friction transferred angular momentum. The Moon helped set the pace at which Earth's axis precessed. Impacts on the Moon preserved records that Earth erased. Moonlight shaped behavior and culture. The pair became so familiar that human language treated them as a natural unit. Now they are neighboring planets in all but size. The Lunar Commonwealth adopts a new official term for its world, Luna. Not because Moon is incorrect, but because Moon has become a category it no longer occupies in the same way. Many residents ignore the change. They continue saying the Moon at home and Luna in law. Earth keeps saying the Moon. The first years of separation are harder for Luna than the operation itself. Transport routes designed around Earth's gravity must be rebuilt. Ships can no longer fall through familiar transfer arcs. Every journey becomes an interplanetary rendezvous. At first, the distance between Earth and Luna remains modest, but their relative positions change continually. Launch windows replace monthly schedules. Travel time varies from weeks to months, then grows as the heliocentric orbits separate. Communication delay increases. A conversation no longer permits interruption. Families send packets, then wait. Live performance becomes exchange. Questions arrive after moods have changed. Apologies cross space while new arguments begin. The long-range archive changes its format. Instead of one shared monthly entry, Earth and Luna record independently and exchange copies when geometry allows. The archive no longer asks only how far apart the worlds are. It asks what each measured while the other was elsewhere. Lunar industry adapts better than pessimists predicted. The world carries enormous solar arrays, mines, sealed ecosystems, and a population trained to repair closed systems. It no longer needs to spend energy climbing out of Earth's deep gravitational influence. From its new solar orbit, Luna becomes a mobile base for exploration and commerce. The advantage does not erase loss. Earth was the largest object in the lunar sky. As separation grows, it becomes a bright moving planet, then a point. The shrinking is faster now than during the centuries of recession because orbital phase adds distance. There are seasons when Earth and Luna are relatively near and seasons when the sun lies between them. Communications route through relay networks. Direct sight becomes occasional. On Earth, the moon also changes from disk to point over generations. At first, it remains visibly round through modest telescopes. Later, it resembles a bright planet whose phases and position no longer follow a monthly cycle. It may appear in evening for months, vanish near the sun, and return in morning. The old constancy is gone. People continue calling moon-shaped objects lunar even when the source of the word is no longer round to the eye. Earth's nights become darker, not instantly. Solar system dust, stars, artificial light, aurora, and human settlement remain. But there is no full moon bright enough to cast a broad natural shadow. No monthly progression of crescent to gibbous to full. No lunar halo around winter clouds. No familiar disk seen through branches. Nocturnal ecosystems continue adapting. Some species decline because the combined loss of moonlight and lunar tides removes cues faster than evolution can replace them. Others thrive in darker nights. Predators that relied on moonlight lose advantage. Prey move differently. Human lighting becomes an even larger ecological force because the natural bright nights are gone. Several nations propose orbital mirrors to recreate moonlight. The project is rejected after ecologists, astronomers, and historians agree on almost nothing except that a manufactured full moon would not restore the system that was lost. Smaller regional lighting projects are built anyway. Some coastal communities illuminate festivals on dates inherited from lunar calendars. Dark sky communities refuse. The oceans settle into a new balance dominated by solar tides, basin resonances, weather, and Earth's own rotation. Tides remain. Their average lunar component is gone, though the details of the transition depend on the path and distance before escape. Spring and neap patterns tied to lunar phases disappear. Solar cycles produce their own rhythms. Coastal charts are rewritten. The change is not universally gentle. Estuaries that adapted gradually during the leaving still face a final loss of the remaining lunar forcing. Sediment accumulates in some channels and erodes in others. Nutrient exchange weakens in tidal wetlands. Human-managed pulses expand. Some coastlines become easier to defend from routine tides and more vulnerable to stagnation. Storm surge remains dangerous because storms do not need the moon. On a beach where Tomas Vale once measured mudflat exposure, schoolchildren open the sealed soil returned from Sellen's lunar archive. The soil is no longer biologically useful. It has been kept too long and too dry. It is scattered into a restored marsh as a memorial. Earth receives Earth again. The vial's glass is placed beside Leora's basalt in the archive. The two materials no longer represent nearby worlds. They represent worlds linked by memory, law, trade, and light time. Earth's axis does not lurch after the moon leaves. The first century without a satellite brings no sudden new season. The obliquity continues its familiar variation. Climate models detect changes in precession frequency, but weather remains dominated by greenhouse gases, oceans, ice, land, and human choices. People who expected immediate chaos accuse scientists of exaggeration. People who expected no consequence accuse them of retreating. The precession watch continues. Its instruments measure Earth's spin axis against distant quasars and planetary orbits. Without the moon's torque, the axis precesses differently. The change alters which secular resonances may matter over long intervals. Predictions diverge after tens of thousands of years, then more. No single forecast becomes destiny. The solar system is not a clock with one future gear train. Tiny differences grow. Planetary perturbations overlap. Earth's rotation changes. Ice sheets and mantle motion alter the planet's shape. Continents move. Human engineering may change mass distribution or climate. The absence of the moon widens the space of possible obliquity histories. It does not select one immediately. Civilization responds by preserving climate adaptability rather than chasing one perfect axial forecast. Seed and ecosystem archives are distributed across latitudes and worlds. Cities designed for wider seasonal ranges. Migration law is treated as planetary infrastructure. Solar management systems remain regional and reversible where possible. The lesson of clear departure survives. Uncertainty does not remove responsibility, and responsibility does not create certainty. Oren lives to see Earth become a star from Luna. She is 126 when she records her final archive entry. Medical systems have slowed aging without making it trivial. She sits in the same hall from which she certified the departure corridor. The windows face a sky where Earth is visible only through an instrument. The telescope shows a blue point beside darkness. Oren does not call it small. Apparent size is not importance, she says. Every navigator knows this. A dim star can decide a course. A world can become a point and remain a home. She pauses to breathe. The first Valas measured distance because they wanted to know where the moon was. We kept measuring because distance became a choice. It was never only a loss. It was also the space in which two civilizations learned whether connection required possession. Her message reaches Earth 8 minutes later. The reply arrives after she has left the hall. No one knows whether she heard it before she died the following morning. The archive preserves both messages without arranging them as a completed conversation. The centuries after Orin are not remembered as one period. Earth historians divide them by climate, politics, migration, and technology. Luna historians divide them by distance from the sun. The residual outward term does not vanish completely after escape. Its exponential growth ends when the Earth-centered orbit ends, but a weaker acceleration remains aligned with Luna's motion around the sun. The source is still unknown. It adds energy slowly, lifting Luna into a wider heliocentric orbit. Each new orbit takes longer. Earth moves ahead and does not lap back into a dangerous encounter. Clear departure did not create that outward journey. It selected the phase from which the journey began. For the first 1,000 years, Earth and Luna remained close enough for regular exchange. Travel windows open every few years, then every few decades. Ships carry people, biological cultures, archives, machinery, and art. The cost rises. Each voyage is debated as if it might be the last, and then another is funded. Eventually, passenger travel ends before communication does. The final ordinary passenger ship from Earth to Luna carries 612 people. Some are returning citizens. Some are researchers. 43 are children. The oldest passenger is a coastal ecologist who has spent her life studying the last unmanaged tidal wetlands on Earth. She brings seeds, preserved plankton, and a jar of estuary mud. At departure, reporters ask why anyone would leave Earth for a world moving outward. She answers, "All worlds are moving." This one admits it. The final ordinary passenger ship from Luna to Earth leaves 21 years later. It carries people whose bodies have been prepared for stronger gravity in rotating habitats. The launch hall remains crowded after the ship departs because families watch the exhaust until instruments, not eyes, are required. Neither voyage is truly final. Emergency, diplomatic, and scientific missions continue. The word ordinary has become the boundary. Before that boundary closes, Earth and Luna build one last shared habitat called Midway. It does not remain halfway between the worlds, because no stable halfway point survives their changing geometry. It is a rotating vessel that follows a solar orbit chosen to meet Earth first and Luna later. For 60 years, it serves as a place where families adapted to different gravities can live together without forcing either body to endure the other world's surface. Midway's gravity changes slowly along its rotating rings. The inner ring remains close to lunar gravity. The outer ring approaches Earth normal. Between them are gardens, clinics, classrooms, kitchens, and wide corridors where people learn how differently a dropped cup can fall. The habitat is not neutral. Earth funds most of it. Lunar engineers build much of its structure. Every wall contains arguments about whose standards should govern air pressure, medicine, education, inheritance, and emergency authority. The first director says neutrality was never the goal. The goal is a place where disagreement can occur without one side being physically unable to stand. Families arrive for stays measured in years. Grandparents from Earth meet children born on Luna. Lunar residents undergo careful loading to strengthen bone and muscle if they wish to enter the higher gravity rings. Earth residents learn the caution required in low gravity, where a careless push can send a body farther than instinct expects. One of the last veiled descendants to use Midway is Darrow, a child of Luna, and his Earth-born cousin Mina. Their grandparents were siblings who chose opposite worlds during the Return Compact. The children have exchanged messages since infancy and meet at age 12. Mina runs toward Darrow in a corridor set to 1/3 Earth gravity. She misjudges her stride, rises too far, and collides gently with a padded wall. Darrow laughs until he attempts the outer ring 2 weeks later and discovers that standing from a chair requires planning. They spend 3 years together. They argue about which world owns the family stories. Mina says Earth kept the garden soil. Darrow says Luna kept the basalt. They consult the archive and discover both objects now sit behind the same glass on Earth, while Luna holds exact records and other materials. Their argument has mistaken custody for ownership in the same way earlier governments did. When Midway reaches the point where their families must separate, Mina gives Darrow a packet of marsh seeds approved for Luna's ecology vault. Darrow gives Mina a small piece of manufactured glass made from regolith collected near the original Far Side driver. Neither gift is ancient. Both are products of worlds that continued changing after the famous objects were sealed. Are we the last cousins to meet? Mina asks. No, Darrow says. How do you know? I don't. I just don't want the sentence. They refuse to record a farewell for the public archive. Their private messages continue for another 80 years, growing slower as the delay increases. Sometimes months pass between answers. Neither treats the silence as abandonment. The delay covenant is a law between worlds, but it began as the ordinary discipline of relationships like theirs. Midway completes 4 encounter cycles before propulsion and maintenance become too costly. It is not abandoned. Its rings are separated into smaller habitats, some traveling toward Earth and others toward Luna. The shared gardens are divided by living cuttings rather than by assigning one side the original plants. No museum preserves Midway intact. Its purpose survives through people who learned that meeting halfway is not a location. It is work repeatedly performed while the location moves. The long-range archive stops using family names as section titles. The veiled descendants object that history has made a dynasty out of people who repeatedly warned against inherited authority. The archive reorganizes around functions: measurement, coast, transit, law, departure, precession, memory. Leora's name remains attached only to the first observation because removing it would hide provenance rather than reduce power. The archive's central question changes again. At first it asked how fast the moon was leaving. Then it asked whether Earth and Luna could separate safely. Now it asks how connection can survive when no journey is routine. Communication remains possible because light does not care about fuel. As Luna's solar orbit widens, delay grows from minutes to hours. Messages become letters again, though they travel as beams. Public conversations stretch across days. Political arguments lose the heat of interruption and gain the danger of decisions made before answers arrive. Earth and Luna establish the delay covenant. Neither world may treat silence within the expected light time as refusal. Emergency requests contain expiration dates. Laws affecting citizens on both worlds cannot take effect until at least one complete exchange has occurred. Military systems are prohibited from interpreting an unanswered message as hostile confirmation. The covenant is violated within a century. It survives because the violation nearly causes a disaster and because both worlds still need a rule for patience. Luna becomes an archive not only by choice, but by environment. Its airless surface preserves structures, impact scars, and sealed chambers. The old lunar cities expand inward, using caverns and excavated volumes. Surface launchers are retired as the outward acceleration becomes too weak to require control and too persistent to stop. Their trenches remain visible from orbit like lines drawn by a civilization that once touched its world's trajectory. Earth changes more quickly at the surface. Coastlines migrate. Cities rise and are abandoned. Ice sheets come and go. Languages split and merge. The absence of the moon becomes old enough that no living culture remembers moonlight except through instruments and art. Artificial satellites take some of the moon's cultural roles. One is placed in a distant Earth orbit with a 29-day cycle, designed to mark inherited calendar dates. It is too small to affect tides or axial precession. Its reflected light is visible only as a bright point. People call it the calendar moon. Astronomers object that it is not a moon in any meaningful dynamical sense. Children call it the moon. The argument repeats every generation and harms nobody. At 10,000 years after departure, Luna's solar orbit lies well beyond Earth's. It is not yet near the giant planets, but the sun appears smaller and cooler. Solar arrays have expanded. Habitats conserve heat. The world carries volatile reserves mined from its poles and imported during the age of close exchange. Comets and asteroids are redirected for water, carbon, nitrogen, and metals. Luna is no longer merely surviving a journey. It is using the journey. Its moving observatories study regions of the solar system from changing baselines. Its industries build spacecraft in low gravity. Some citizens leave for independent habitats. Others remain because Luna is the oldest human home beyond Earth and the only one whose geology contains both primordial history and the marks of the leaving. Earth receives compressed archive updates every year by Earth time. The packets take longer to arrive. Each contains measurements of Luna's orbit, the residual acceleration, ecological status, population, and copies of public memory. Earth sends equivalent records. No one reads all of them. Institutions maintain the exchange because unread continuity can still matter. A future crisis may require old data. A person may search for an ancestor. A society may need proof that another society once answered. At 40,000 years after departure, the residual force weakens again. It has not reversed. Luna's outward migration slows, but the new solar orbit is securely larger than Earth's. The distance varies through geometry, yet never returns to the old neighborhood. Clear Departure's immediate purpose has been fulfilled beyond the lifespan of its designers. On Earth, the precession watch records the first unmistakable departure from the narrow obliquity behavior familiar to the lunar age. The axial tilt reaches a value outside the old range and remains there for thousands of years. The change is not a flip. Earth's tilt moves from about 23 degrees toward 26, then 28. Summers at high latitudes receive more intense sunlight. Winters become darker. Monsoons shift. Ice responds. Ocean circulation reorganizes. The process unfolds over millennia, slow enough for forests to migrate where corridors exist, and fast enough for species trapped by cities or mountains to disappear. Civilization does not face one global choice. Northern settlements redesign buildings, agriculture, storage, and energy systems for stronger seasons. Some regions benefit from longer bright summers. Others suffer drought or winter isolation. Migration increases. Political systems that planned for fixed climate zones fail first. The old lesson returns. Slow change is not harmless change. It is change that offers time, and time can be used or wasted. People ask whether the missing moon caused the new tilt. The honest answer is that its absence changed the spin axis dynamics and allowed a wider set of responses to planetary perturbations. The particular path also depends on Earth's rotation, internal structure, orbital variations, and the gravitational architecture of the solar system. The moon's departure did not push the axis like a hand. It removed a stabilizing relationship from an already complex system. Earth does not become uninhabitable. It becomes differently seasonal. At 90,000 years, the tilt returns toward 24 degrees. Later it rises again. Climate cultures learn to think in precession eras rather than permanent zones. Long-lived infrastructure is designed for ranges of latitude and sunlight. Seed libraries migrate. Cities maintain northern and southern partner sites. The most valued maps show not borders, but future climate corridors. Some historians claim the moon's loss forced humanity to become adaptable. Ecologists reply that adaptability was always required and often imposed on those with the least power. The debate becomes part of school curricula. Luna watches these changes from increasing distance. Its own axis and rotation have evolved under solar torque and the remnants of its earlier history. Earth is no longer the body that dominates its sky or tides. Luna has no oceans, but its interior still flexes faintly under the sun and passing planets. Moonquakes continue for reasons that have nothing to do with homesickness. At 120,000 years, an archive keeper on Luna named Sava Arun discovers an error in the clear departure record. One Farside driver's final mass total was copied incorrectly in 3 authoritative summaries. The raw instrument data contains the correct value. The error did not affect navigation because the orbit was measured directly, but generations of histories repeated the wrong number. Sava publishes the correction. Earth receives it 14 hours later. The correction is small enough to seem absurd after so much time. It matters because the archive was founded to preserve the difference between what happened and what people preferred to remember. Sava records a message beside Leora's first entry. The first distance was 7 millimeters. This correction is smaller in consequence. Scale does not decide whether accuracy matters. The long-range archive has no central building by then. Copies exist on Earth, Luna, Mars, habitats, and interstellar probes. Consensus is maintained through comparison rather than one master record. Some copies diverge. Some are lost. A memory can be distributed and still require care. At 160,000 years, the archive is asked to do more than correct a number. Earth is passing through a high obliquity climate phase. Strong seasonal contrasts have moved temperate coastlines and changed the timing of river flow. An old chain of restored estuaries along the southern edge of a continent begins failing in a way engineers do not understand. The water gates work. Sediment moves. Salinity follows the planned range. Young marsh plants grow for several seasons and then collapse. The missing part is microscopic. During the last lunar centuries, coastal ecologists had preserved not only seeds and animal genomes, but complete living communities of bacteria, fungi, protists, and tiny invertebrates from tidal mud. Most Earth archives later reduced these communities to genetic records because maintaining thousands of evolving ecosystems seemed unnecessary. Luna kept several as sealed research ecologies, partly because its biologists were studying how communities change in closed habitats. The failing Earth estuaries descend culturally, though not biologically, from the coast where Tomas Vale once worked. Their managers search the Long Relation archive and find references to an intact pre-departure mudflat community on Luna. They send a request. The message takes 17 hours to arrive. Earth asks for complete genomic descriptions, metabolic measurements, environmental histories, and, if possible, living samples. The request is not an emergency in the old sense. No city will die that week. The estuaries may fail over decades, taking fisheries, storm protection, and migratory habitat with them. The timescale makes urgency easier to postpone. Luna answers after another 17 hours. The data can be transmitted immediately. The living community cannot. It includes interactions no genome file describes fully, viruses not yet classified, dormant forms, chemical gradients, and behavior produced by the community rather than one organism. A synthetic reconstruction might work. It might also create an ecosystem that looks correct in a laboratory and fails in open mud. Luna offers to send a physical ark. The fastest safe vessel will take more than 300 years to reach Earth because Luna's outward path in Earth's solar orbit are no longer convenient to connect. A faster craft could be built, but acceleration, shielding, deceleration, and biological stability increase costs sharply. 3 centuries is considered reasonable for a project intended to restore coastlines that may be used for millennia. The proposal produces an argument on both worlds. Some lunar citizens say Earth had centuries to preserve its own living diversity and should not treat Luna as a backup warehouse. Some Earth citizens say funding a mission whose sponsors will all be dead at arrival is ceremonial waste. Biologists warn that releasing ancient communities into future environments may cause harm. Coastal residents ask why their homes must justify a timescale that orbital observatories accept without question. The archive contains Ceylan-sealed soil, the estuary mud carried on the last ordinary passenger ship, and records of the original ecological cultures. None of these objects belongs to one generation. Their preservation was already a decision made for unknown people. The Joint Council approves the vessel under strict conditions. Earth will first use transmitted data to test synthetic communities. The physical arc will contain multiple isolated samples, not one supposedly perfect original. Nothing will be released automatically. Future Earth authorities will decide whether conditions still justify use. Luna will retain its own cultures. The mission is named Reciprocity. Building it takes 19 years. Reciprocity is small compared with passenger ships. Most of its mass is shielding, thermal control, redundant power, and rotating culture chambers. It carries estuary communities, seed banks, preserved plankton, and several organisms Earth did not request because lunar ecologists believe future restoration may require relationships no current model recognizes. The manifest explains every addition. Nothing is hidden behind the word natural. At launch, nobody alive expects to see arrival. Sava Arun records the departure. A message says what we know. A vessel admits that some knowledge has a body. The ark leaves Luna on a long inward trajectory. It does not chase Earth's current position. It aims for where Earth will be after more than 3 centuries. Navigation corrections are planned by institutions that do not yet exist. Every 50 years, Luna and Earth exchange custody statements. If either civilization loses interest, the vessel can enter a safe solar orbit rather than arrive unwanted. On Earth, the estuary program continues without waiting. Synthetic microbial communities restore part of the missing function. Marshes return in some regions. Others fail. Engineers learn that the old ecology cannot simply be pasted into a changed climate. The physical arc becomes less a rescue and more a future comparison. Critics say this proves it was unnecessary. Scientists reply that learning before arrival does not make arrival meaningless. 112 years into the voyage, Reciprocity loses contact. The last transmission reports a power imbalance in one shielding layer. Earth and Luna aim a raise toward the predicted path. No response arrives. The vessel is too small and dark to locate easily. For 9 years, the archive lists it as missing. A tracking cooperative near Mars finds it accidentally while surveying debris. The Ark has entered safe mode and stopped its main beacon to conserve power. Its biological chambers remain stable. A repair craft replaces a failed. Researchers compare the living samples with reconstructed Earth systems. They discover that one group of viruses once dismissed as incidental regulates bacterial populations during salinity shocks. A tiny burrowing animal alters oxygen flow through sediment in a way no synthetic model reproduced. Some old organisms would be invasive under current conditions and remain sealed. Others can be introduced experimentally inside enclosed marshes. The first release is smaller than a bathtub. Mud, water, microbes, spores, and invertebrates enter a controlled tidal basin. Scientists observe for 20 years. The community does not recreate the ancient coast. It combines with current organisms and forms something new. Several functions improve. Nutrient cycling stabilizes. Plant roots survive seasonal extremes more often. The result spreads cautiously to other restoration sites. Reciprocity does not save Earth's coasts. No single vessel could. It returns relationships that had been lost and gives future ecologies more ways to respond. Earth sends Luna a message of receipt. By then, the one-way delay is longer, and the people who maintain the source cultures belong to later institutions. The message includes no claim that the debt is repaid. Earth received living material. Release remains limited. Several functions recovered. Archive lineage continues. Luna answers. Keep what works. Preserve what does not. Send forward what you learn. The exchange becomes one of the most studied records in the archive because it demonstrates that distance can turn aid into an agreement among strangers across time. The sender cannot control the use. The receiver cannot thank the people who began the act. Responsibility is carried by institutions that repeatedly choose not to abandon it. At 200,000 years, Luna has become a small, wandering civilization in the outer solar system. The sun is bright, but no longer large. Its surface temperatures are lower. Habitats depend on fusion, stored energy, and carefully managed sunlight. The ancient solar arrays near the equator are monuments. New power systems lie beneath the surface. The residual outward term is now weaker than many natural perturbations, but its integrated effect has carried Luna far beyond the orbit from which it began. Encounters with minor bodies are planned years ahead. A close passage by an icy object provides material and alters Luna's course slightly. Engineers debate whether deliberate gravitational encounters violate the principle that no generation should claim permanent control of the world's path. The answer has changed since Clear Departure. Clear Departure addressed a threat to Earth and Luna. Later maneuvers address survival, resources, and navigation. Luna's citizens establish a rule that no trajectory change may be justified only by the needs of people not yet born, and none may ignore them either. The wording satisfies nobody and prevents several reckless proposals. Earth appears in Luna's largest telescopes as a pale point near the sun. Direct messages require more than a day. The two civilizations have changed beyond easy translation. Languages share roots, but not assumptions. Political systems recognize one another through treaties updated over centuries. Family lines no longer bridge the worlds in ordinary memory. The archive does. A child on Earth can still hear Orin say that apparent size is not importance. A child on Luna can still watch the 1-second final totality reconstructed from independent recordings. Neither child experiences the event as personal loss. It is origin history. At 300,000 years, Earth's obliquity enters another high phase. The tilt approaches 32 degrees in this branch. Polar summers are intense. Polar winters are long. Ice becomes strongly seasonal in regions where it once persisted. Tropical annual sunlight changes less than high-latitude seasonality, but circulation carries effects everywhere. Human and non-human life has had time to evolve, migrate, and engineer responses. The biosphere is not the same biosphere that knew the moon. Some lineages survive. Others are represented only in genetic and ecological archives. New species use the solar tide, artificial wetlands, and seasonal light cycles that once would have seemed extreme. The moon's departure is not the only cause of anything visible. Continental drift has changed ocean basins. Mountain ranges have risen and eroded. Atmospheric composition has varied. Technology has altered habitats. The absence of lunar stabilization remains one part of the long dynamical background. This complexity protects the story from becoming a fable in which one missing object explains all future history. It also makes grief harder to assign. People on Earth still create images of the old full moon. Some are scientifically exact. Others show it too large, too bright, or in impossible phases. Artists defend the distortions. Memory has never been an ephemeris. One school maintains a chamber illuminated by reconstructed moonlight at the spectrum and brightness recorded before the leaving. Students enter after dark. A round source rises behind a simulated horizon. Shadows form softly. The light is far dimmer than many expect. Some students are disappointed. Others remain until the chamber closes. They say the important thing is not brightness. It is the knowledge that the light once crossed from sun to moon to earth, touching two worlds before reaching an eye. At 680,000 years after departure, Luna crosses another boundary. Its residual outward acceleration, small but persistent, has added enough heliocentric energy that the sun can no longer keep it on a closed orbit. The transition is gentler than the escape from Earth. There is no chaotic three-body corridor and no need for an 11-day intervention. Luna's path simply widens until the calculated orbit becomes open. It will pass through the outer solar system and continue into interstellar space. The sun will remain the brightest star behind it for a very long time. Planets will become points and then difficult points. The Oort cloud is not a shell crossed in one season, but an enormous, sparse region extending through years of travel. Luna will encounter no wall labeled edge. The outward term has finally made the title literal within the chosen branch. The former moon is not merely on a different solar orbit. Its distance from Earth will continue increasing without a planned return. No finite measurement can prove forever. Stars move. Galaxies evolve. Unknown forces remain unknown. But every model consistent with the premise shows the same immediate future. The separation grows. Luna has prepared for this for hundreds of thousands of years. Its cities no longer depend on sunlight. Fusion systems, deep thermal storage, and imported volatiles sustain ecosystems beneath the surface. The inhabited world is distributed through caverns and orbital structures bound to Luna itself. Its population is smaller than Earth's and larger than many ancient planetary civilizations. Some citizens leave for other stars on faster craft. Others remain because a moving home is still a home. The decision to remain is no longer framed as refusing evacuation. There is nowhere that every person is expected to prefer. Earth sends a message acknowledging the solar escape. It takes 11 days to arrive. The delay covenant is revised for interstellar time. Silence is measured in months. Shared decisions become rare because the worlds no longer govern the same immediate systems. The covenant's purpose changes from preventing accidental conflict to protecting interpretation. A message answers the world that sent it, not necessarily the world that exists when it arrives. Earth and Luna include context records with every major communication. Population, law, language, climate, technical standards, and known emergencies travel beside the main text. Translation systems help, but they do not erase divergence. Each civilization maintains historians whose profession is not studying the past, but explaining the present to a distant correspondent. The long-range archive becomes the long relation archive. Some archivists object to changing the original name. Others point out that range was always a relationship expressed as distance. Both names remain in use. On Earth, the moon is no longer visible in ordinary telescopes. Its predicted position is known from its own beacons and from weak observations against background stars. Without transmitted signals, finding it would require enormous instruments and patience. The object that once dominated the night sky has become one of the faint moving points in a crowded universe. The night itself is not empty. Earth has new satellites, habitats, rings of instruments, and occasional comets brighter than the ancient moon. None raises the same tide or holds the same history. People no longer expect one object to replace another perfectly. The old full moon belongs to a past environment, like vanished coastlines and extinct species. Earth's obliquity continues wandering through the broader dynamical space available without lunar stabilization. It does not move randomly from year to year. It follows long resonant patterns shaped by planetary gravity and Earth's own changing spin. Some eras have severe seasonality. Others resemble the old lunar age closely enough that reconstructed landscapes can flourish at familiar latitudes. Life persists through change and loss, never as proof that loss is harmless. Many ecosystems are managed across millennial cycles. Others are allowed to migrate. Some regions are abandoned when climate corridors move. Cities are designed as archives of materials rather than monuments that must stand forever. A building may be planned for disassembly after 800 years. A forest may be planted with routes for descendants to move poleward or equatorward. Permanence becomes less admired than continuity. The leaving is taught as one of the events that changed civilization's understanding of stability. The lesson is not that nothing lasts. The lesson is that lasting often means changing form without hiding the cost. Earth lasted without the moon by becoming a world of stronger adaptation, solar tides, changing seasons, and inherited memory. Luna lasted without Earth by becoming a closed moving world, then an interstellar one. Island is 34 and has never considered the moon a missing object in personal life. She grew up beneath a dark natural sky. Lunar phases are history. Total solar eclipses are impossible without artificial occulting craft. Tides come from the sun, oceans, and local geography. Seasonal planning includes axial states that ancient people would have called unusual. She still knows Leora's first measurement by heart. The anniversary exchange is technically unnecessary. Earth and Luna communicate through broad arrays, relay probes, and coded transmissions. A narrow optical pulse is chosen because the relationship began with laser ranging. The beam cannot rely on an old reflector. The Apollo and later arrays are buried, damaged, or pointed into useless geometry on a world that no longer keeps one face toward Earth. Luna will detect the pulse with a phased receiving field spread across its surface and orbital structures. After reception, people will choose whether and how to answer. This distinction matters to Island. The first lunar return was automatic. Light struck a corner cube and came back according to geometry. The final scene of the anniversary will not be a reflection. It will be correspondence. On Luna, the receiving coordinator is Tavi Son, an archivist and navigation physicist. She was born beneath a sky where the sun is a sharp white point, still far brighter than every other star, but too small for an unaided eye to resolve as a disk. Earth cannot be found without a chart. Tavi has studied Earth history for 40 years. She understands ancient oceans mathematically and has never smelled salt water. Her workday begins 23 days before Island sends the pulse because that is the current one-way light time. Earth and Luna synchronize through predictions rather than live confirmation. Each side knows the planned emission window, wavelength, pulse pattern, and uncertainty region. Earth will aim at where Luna should be when the light arrives. Luna will orient receiving fields toward where Earth was when the light left. The geometry resembles conversation with ghosts and is entirely ordinary to both civilizations. Island spends the morning checking clocks. The clocks are no longer defined through Earth's rotation. They are linked to atomic and pulsar standards distributed among worlds. She checks atmospheric turbulence, adaptive optics, beam safety, and the predicted positions of every craft near the path. The pulse carries too little energy to harm anything, but procedure survives because care should not depend on danger alone. At the memorial marker, school groups gather. They cannot see the beam. Public displays show a reconstruction. Some students ask why Earth does not simply send the archive message through the normal network. Island answers, because method can carry memory. A student asks whether that is efficient. No, the student approves. On Luna, Tavi checks a copy of Leora's first entry. Language has changed so much that the original requires study. The archive preserves pronunciation models, but nobody knows whether they reproduce the exact voice heard in the observatory. Tavi listens anyway. The moon has moved farther than expected. Nothing visible has changed. That sentence is how this story begins. Tavi has heard it hundreds of times. On this day, the words feel addressed to her. At the scheduled moment, Island places her hand on the emission control. The gesture is ceremonial. Multiple systems and human observers must agree. The beam array has already aligned. The pulse sequence is simple enough to survive partial loss. A timing preamble, the anniversary number, the first measured residual, the current Earth state, and one sentence. The answer from Luna is already being copied across Earth. It will enter schools, arguments, songs, and private messages. Some people will call it proof that distance never matters. That would be false. Distance shaped every part of the relationship. Some will call it proof that nothing is ever lost. That would also be false.